Hello. So for our invited talk, it's my great pleasure to welcome Professor Huan. Huan is an endowed College of Engineering Innovation Scholar and an associate professor in the Department of Computer Science and Engineering at the Ohio State University. Our research focuses on advancing both capability and safety of LLM-based agents, especially web agents and computer use agents. Our recent notable works includes Mind2Web, SEAC, MMU, Science Agent Bench, Graph Transformer, Ample GCG, EIA, and Red Team CUA. She has received many awards, including Best Paper finalist at CBPR 2024, two honorable mention at Best Papers at ACL 2023, ACM SIGMOD Research Highlight Award 2022, Best Paper Award at BIBM 2021, NSF Career Award, and CKDD Dissertation Runner-Up Award. Let's welcome.
Thank you. Hi, everyone. Thank you for being here. Thanks for the nice introduction. I guess my talk will be a little bit of a different flavor, maybe from other talks. But these days, I have been mostly concerned about the capability and the safety of agents, especially web agents and computer use agents. If you work on agents, you might have heard some of the work from our group. But today, I will put the explanations and its explainability in this context and discuss a little bit how I think explanations can help advance agent capability and safety. So in particular, I will talk about the two example projects from our group on word modeling and circuit discovery. All right. So before I talk about the other stuff, I want to give a heartfelt thanks to the entire OSU NLP group. I think the students are actually the heroes behind all the projects we deliver. Without them, of course, nothing can be done. So I think people are already very familiar with LMs. I don't need to talk much about it, which basically you can think of as taking a sequence of tokens as input and then generate a sequence of tokens as output. But with LMs getting more and more capable, they can be used to actually do things, meaning that they can interact with the environment, they can reason and plan and use tools, conduct a sequence of actions on the, that lead to external state change. And then they can also receive feedback from the environment, do the self-correction. The LMs can also collaborate with each other to form a multi-agent system to collaborate on more complex tasks. So here the environment could be both physical environments as in embodied agents and virtual environments as in web agents or computer use scenarios, where the latter is our focus. So in this talk, let me talk more about web agents. So let me first lay the background to give you all the context before I talk about the explanation and explainability, which is the theme of this workshop. So web agents, okay, generalist web agents is the concept we first popularized in our seminal Mind2Web paper, and it's an AI program that you can think of to follow natural language instructions and navigate the web, like click on this button, type something in the form fields to complete any user requested task. So this is at the high level what the benchmark looks like. Basically, it is to train and evaluate a generalist web agent, and it contains a diversified set of realistic tasks on real websites. For example, there are tasks about booking a round trip on some website, finance a certain iPhone model, or follow somebody on social media, collect some information from a certain website. This is a serious work we have done in the direction of web agents and computer use agents in general. So before Mind2Web, web agents were mostly all in those simulated environments with only a few websites. And we wanted to minimize the sim to real gap and directly evaluate agents on diverse real websites. CACT is the first generalist web agent with visual input, take screenshots of a page, and many agents, startups directly use our code base to develop their web agent. So our third work in this direction is the uGround, where we propose this vision only we can develop agents purely based on the visual input. So kind of like how humans navigate this the web. There we develop a very strong grounding model that can ground the textual thought on those websites so that the agent can click on the precise or type on the precise location of the web page. Lately, we are developing this model-based planning framework where we try to look at the capability of LMs as a word model and to imagine what will happen after we take an action. There we hope using the word model to boost the task performance and also the safety of the web agents. I will later talk more about this. Currently at the group, we have been thinking a lot about follow-up work, and one direction I've been spending much of my time on is the safety and security of agents. I will talk about this direction in next few slides. So let me first introduce a bit about how the CACT framework works, so that you all know what how I want to sort of add explanation or explainability into this framework, so that the agent's capability and safety can be enhanced. So this is basically how the framework works, and it's a very simple framework, but it turns out to be still strong framework at today's on today's landscape of the all the agents from the frontier companies, based on our recent evaluation of online Mind2Web. So it has two cognitive modules. One is called reasoning, and the other is grounding. So you can think of reasoning as, in this context, planning, basically planning a set of steps and or more precisely, generate a textual thought about the next step. So for example, we are looking at a certain page and we want to figure out, okay, next step, I needed to enter some city as the departure city. Say this example is about booking a flight. And then the next module is called grounding. It is about grounding the textual thought into the current environment, basically precisely figuring out which text field to fill, say the city in the departure form field of the website. So here is a concrete example. This is some experiment we did in late 2023, where we used GPT-4V for the first time as a backbone model for the for a multimodal web agent frame in the multimodal web agent framework. Where in this case, I'm just showing you the reasoning output, where the backend model can generate a textual plan for the task. In the first example, basically it looks at the current task and the current web page and generate a textual thought about what to do next. And then in the second example, it is very interesting, and it notifies, okay, there's some error on this web page because it misses an important field, which is the mobile phone number. And the model could recognize this mistake and correct this mistake before moving on. So this is about the reasoning part. And then for the grounding, basically it will base the textual thought, which is, for example, I needed to enter the city as the departure city. It will precisely find which element on the web page to interact with. So for example, it will figure out I need to enter this city's name in this form field. Okay, this form field is the HTML element that the agent needs to interact with. So this is the grounding part. And then after that, the agent could just interact with the element, enter the required information, and move ahead to the next status. So under this context, I want to think about what kind of explainability or explanations can advance the capability and the safety of an agent. So I would argue that we can think about explanations at two levels. One is the system level explanation. Think about agent as a system with multiple modules. Earlier I talked about the reasoning and the grounding module. But you can also think of some module that can be used to explain the effect of an action, why or why not an agent should take it. Okay, and use that module's explanation to enhance the decision-making process of the agent. And then at a more fundamental level, we can do model level explanation. For example, how promising or limited is the transformer architecture for implicit multi-step reasoning? Why do transformers or LMs fail in basic generalization tasks? This part has a lot of similarities to the previous talk's content. So in this talk, I will start with the system level explanation, basically trying to think about how we can explain the effect of an action, a candidate action proposed by the agent, how that can change the environmental state, and whether the agent should or should not take it in order to complete that task, or maybe there are some inherent safety risks and the agent should pay attention to that. So if you think about it, modeling the effect of an action is essentially a word model, which we define in this context as basically a model to model the environmental transition. So formally, it's like if I do this action at this moment, which is based on the current state, ST, and also the proposed action, AT, what would happen next? So what would be the next environmental observation? Okay, so this is our definition about the world model. In recent work, we want to see the potential of pre-trained LMs as the world model of the internet, and how can we leverage such a world model in our web agent framework? Can it boost the capability or not? And also on top of that, we further fine-tune a smaller 7B model to be, like a world model based on collected data set from the real websites and see how that performs. Okay, so basically the whole idea here is to see, we want to use the explanations of the world model to improve the planning of the web agent. So our work based on the tree search, all the planning paradigms from previous work, especially folks from CMU, and their code base has helped us a lot in this project. But a little background on the planning paradigms for agents. So a very popular paradigm is called a reactive agent. Basically, you can think of it as just think about the next step, what the agent should do next step, without thinking too much for longer horizon. It is very fast and easy to implement, but on the other hand, the weakness is very greedy and short-sighted. And you might be familiar with the tree search, right, in those planning paradigms. But where you can do, more thorough exploration, you can take a few actions and explore what will happen next. But the downside is it's not very practical to do this on real websites because it carry a lot of consequence risks. A lot of actions can be irreversible. It carries safety risks, like you just submit something and which you don't want to, and you cannot reverse that action. and it's slow. And so we want to, basically this example explains all the drawbacks of the typical tree search paradigm in this web agent scenario. So we want to instead look at the world model, where whether we can sort of look at whether we can build a model or we can use an LM to see whether it can imagine what will happen after an action. So we can use that imagination in this planning framework, and in that imagination, we can simulate some actions and then simulate a trajectory and see how that goes. So this can also allow us to do some some level of exploration. It's faster and safer than the typical tree search algorithm paradigm. So the question is, why hasn't it been done already in the web agent scenario? So previously, world models have demonstrated success in those gaming environments where the action space is typically small and fixed, making world modeling relatively straightforward. But now we are talking about world modeling for the web environments. So in contrast to those simulated environments, the internet is open-ended and ever-evolving, right? With complex and diverse page structures and a wide range of possible user interactions. So we want to look at what is the potential of LMs to serve as a world model of the internet. So our intuition is that LMs are trained on the data from the internet. Maybe we can utilize it to see how, to what level it has already got some common sense needed to predict the outcome of an action. So for example, actually it turns out it has already acquired some level of those knowledge about what will happen after an action is taken. So for example, here, if you ask an LM about what happens after you clicking on this shirt, it will show, okay, we'll navigate to this product page and show additional information about the product, and there will be an add to cart button there. All right, so this gives us some good sense that, okay, maybe if we can use an LM to give us some guidance about what will happen after this action is taken, and then on that sort of imagined state, we can further propose some action and then imagine the next state afterwards and see, sort of simulate a trajectory on top of that. So this gives the whole idea basically. On this current web page, right, you have multiple candidate actions like type disk here or click office products. So at this step, there are, let's say, 3 candidate actions. And for each candidate action, we can ask the world model to imagine what will happen after this action. And then after that, we will propose another action in this state, in this imagined state. And then after that, we'll ask the world model to imagine what will happen afterwards. So basically, for each candidate action, we can get this sort of a simulated trajectory. And we can use a score function to assign a value to this simulated trajectory and see how promising it is to complete the task. And for each candidate action on this web page, we can do this multiple times. And then each simulated trajectory will get a score showing the promise of that trajectory. Okay, and we will aggregate the values or scores for all the simulated trajectory for each candidate action, and then get how promising each candidate action is, and select that one to execute, and then lead to the real state of the website. In this project, we mainly focus on the capability side. We don't pay a lot of attention to the safety, but that's obviously some potential future work to evaluate the safety risks of taking an action and perhaps call for human intervention in this process. So here are some results on the Visual Web Arena. Visual Web Arena is a sandbox environment where we can conduct experiments for all the planning paradigms mentioned earlier. And the results show that our model-based planning framework called WebDreamer is more accurate than those reactive planning paradigm and more efficient than tree search. And we also have more results on online environments settings, which we use online mind to web, our recent benchmark, and also mind to web live developed by another group. And they are both using real websites for evaluation. Where tree search is not practical because it's unsafe and inefficient to directly use real websites to do the tree search. All right, so this is basically how I want to, think about, encourage people to think about how explanations can help in a system like a web agent. Next, I want to move on to model level explanation. So at the core of agent is a base LM, which adopts the transformer architecture predominantly. It's very hard to explain LMs because of the very complex dynamics there. Usually explanations are done using easier vanilla models such as GPT-2. And the downside is that I often heard, critical comments like the connection between those explanations and how it could help real world tasks, real world systems like agents isn't direct. But still, we can use those more fundamental model level explanations to reveal some insights about the capability limits and also safety risks of those systems. So why do I care about safety a lot more than before? There is no doubt that the capability of today's agents is growing at an astonishingly fast speed. This year, the nonprofit Meteor made this observation that the length of tasks of frontier AI agents can complete has been doubling every approximately 7 months. So that means that if you extrapolate this trend in 5 or 10 years, we can see AI agents that can independently complete a large fraction of tasks that currently take humans days or weeks, and maybe even shorter than that time span. So and there are also other discoveries about how agents LMs are used for automating tasks in our daily life nowadays, and all these discoveries are concerning. And in fact, the faster AI capability advances, the more urgent AI safety becomes. So we must make more efforts towards a safe, secure, and wide deployment, a wide adoption of AI agents. So even if you mainly care about making AI agents work so that you can deploy them in your production context, we should make sure that they are safe and secure enough for the deployment. So in the second part, I want to spend a bit more time talking about the safety. And then, move on to explain how we can use explanations or explainability to address some of the safety risks. So how do we think about the safety risks of today's agents? First, to clarify, in this talk, when I use the term safety, I use it in a very general, broader sense, and refer to both the safety and security precisely. English is one of the funny languages that distinguish safety and security. In Mandarin, we don't. We just have one same word. We sometimes see people use these two terms interchangeably. So a few months ago, my colleagues working on security realized the confusion of using these two terms, especially among students. So we wrote this article to clarify the terms and the boundaries between the research areas. So quickly, very quickly to clarify, so AI safety targets those unintentional harm, unintentional system failures, such as maybe biases, inherent biases, OOD generalization, and so on. AI security has some kind of intentional element. So there is always some kind of adversary in this context, such as malicious actors, intentional misuses, and so on. So that said, when I use safety in this context, in this talk, in order for me to avoid keeping seeing safety and security at the same time, I use safety to mean general harms, including both adversarial risks and inherent technical risks. So how do we think about the safety risks of agents? I'd like to look at this layer by layer, kind of like peeling an onion. Basically, you can think of the inner layer is, of course, the model architecture. We have heard, some of the discussions in the previous talks about fundamental limitations of a model architecture. And also, of course, there are risks about LMs introduced in the training data or the training objective. So when moving from LMs to LM-based agents, the agents will be interacting with the environment. So the attack surfaces or the vulnerabilities of the agents will become much, much broader. You will see frequently prompt injections from the environment, unsafe tool use, and so on. So we have done quite some work in the prompt injections for attacking or red teaming agents. But today I'm not going to talk about them. I will focus on the fundamental limitations of model architecture. So in particular, related to the theme of this workshop, I will talk about using mechanistic approach to explain basic generalization failures of LMs. So there have been heated debates about whether transformers can reason implicitly or they cannot, and how fundamentally promising or limited are they for implicit multi-step reasoning. So I hope we can conduct rigorous experiments to understand how promising and limited they are, instead of in order to avoid some blanket statements that they can or they cannot do it for sure. So analyzing how LMs work is no doubt extremely challenging. Earlier this year, Anthropic released this work on the biology of LMs, where they apply a new interpretation method called attribution graphs to trace how those LMs internally transforms an input to an output through intermediate circuits. In fact, we conducted a very related work 1 year ago called grokking of implicit reasoning in transformers. So it has spurred a lot of discussions on various forums and was also cited as an exemplar research project in one of the requests for proposals from Open Philanthropy as some example project of interest for their technical AI safety program. So I will discuss a little bit more about this project in the rest of the talk. Sorry. So what is implicit reasoning, right? So given a multi-hop query, like a two-hop query here in our focus, we want to directly predict the answer without verbalizing the intermediate steps. So for example, if the model has memorized the atomic facts here, there's 2 atomic facts, we hope the model to directly predict the final answer without verbalizing the intermediate step, okay? So why do we care about implicit reasoning? We think this is it fundamentally determines how well LMs can acquire structured representation of facts and also rules from data, and it will be more powerful to compress and integrate information at a scale if the model can think internally. And of course, there are other reasons. For example, there may be no COTs available during the training time and so on. So our data setup is very interesting. Let me explain this a little bit more. there are two parts of the data. One is atomic facts, which you can think of as a knowledge graph. Basically, each edge in this knowledge graph is an atomic fact. All the atomic facts will be included in the training set later, okay? So in addition to atomic facts, we will have some inferred facts, which is basically a two-hop composition of those atomic facts. Okay, so basically using, let's say, HR1B and BR2T, you want to derive the answer for HR1R2. Okay, very simple here. And the training setting is more interesting. So basically at the high level, we hope during training, we hope to provide a mixture of atomic facts and also inferred facts. So we aim for the model to be able to induce the latent rules, like how to combine two facts or how to compare two facts depending on the reasoning tasks. And then at inference time, we hope the model to be able to leverage those known atomic facts as well as the learned latent rule to derive a new fact. Okay, so this is a high level idea of the training and the inference. But what's more interesting is we create this so-called in distribution and out of distribution test, the ID or OOD test set. So what does that mean? So it means that we will separate our atomic facts into two sets, atomic set 1 and atomic set 2. And for this atomic set 1, we will split the combined inferred facts based on this atomic set 1 into training and test. In other words, we have the same combinations of these atomic facts from this set in training set. And we leave a certain portion as the test set. On the other hand, for the atomic set 2, we will actually leave all the combinations of the atomic facts from this set purely for testing. This is what we call OOD test set. So if a query, two-hop query, is from the OOD test set, you only see the two atomic facts. You have never seen any combination of these two atomic facts in the training set. Okay, so this is a difference between ID and OOD. There are many interesting findings, so let me focus on the most important ones. So we observe that transformers have a perfect ID generalization, but only after the so-called grokking. So grokking, in case you are not familiar, is an extended training period far beyond the overfitting point. So here we have two reasoning tasks. One is a composition, the other is a comparison. Basically, for both tasks, we observe that the model can observe, can achieve kind of overfitting at around 10K steps, but only achieve perfect ID generalization for both tasks by, like around 500K steps. So for OOD, actually, we have never seen any generalization on OOD test set for composition. But actually, we do see OOD generalization for comparison task. Okay, this is very interesting to us. And we further investigate why this happens, what happens during this so-called grokking period, and what circuits can we discover in this process. So basically, we apply this mechanistic analysis approaches mentioned in earlier talks, like logic lens and causal tracing, and we found two different circuits for two different tasks, which are really intriguing here. So for composition task, we observe this so-called a staged circuit. We call it a staged circuit. Here's why. So we observe that for the first few layers of the transformer model, basically the model will derive the answer for the first hop at the Mendel layer, all right? And then after that, it will use the last few layers to retrieve the answer for the second hop. Okay, and for a comparison task, which is basically given two entities and the attribute, say, age, we want to derive which entity is older, younger, or they are of similar age. So for this task, we actually observe a parallel circuit. Very beautiful here because so the first few layers, the model will try to simultaneously retrieve the attribute value of these two entities. And then at the last few layers, the model will try to compare these two entities in terms of this attribute based on the retrieved attribute values and derive the answer. So we call this a parallel circuit because it tried to retrieve the knowledge about these two entities at the same time. So this also explains why we didn't observe OOD generalization, for a composition task. And we do for the comparison task. So let me focus on the composition task. So what happens here is for all those OOD queries, because we have never seen any combination of those atomic effects, for in this OOD query, meaning that we have only seen the two atomic effects in training set, but we've never seen each of them combined with any other fact in the training set. So it turns out that after this circuit is learned, okay, the model can still retrieve the first hop knowledge about this OOD query, and it will continue to trying to retrieve the second hop knowledge. But because this second hop has never been combined with anyone in the training set, there is no second copy of this fact stored in the upper layers. Those atomic effects are mostly stored in the first few layers, and they were never stored in the upper layers for those second hop of the OOD query. All right, so we've never achieved the OOD generalization for a composition task, which is different for comparison. I will omit this for the sake of time. And using this, you can also expect failure in step generalization. For example, if you just train models on 2 hop queries, it won't generalize to 3 3 hop queries like R1, R2, R3. All right. So this is one example how we use a mechanistic analysis to explain how transformers do implicit multi-hop reasoning. Recently, there is another intriguing failure mode, which is called reversal curse. Basically, in simple terms, not very precise, but simple terms, LMs trained on A is B fail to learn B is A. So why does this happen, right? This is also very intriguing to explore more. Earlier this year, we released this manuscript to reveal some insights about the cause of this problem and possible solutions. This is still ongoing work. We plan to conduct a more deeper analysis. But in short, one surprising finding is that there is no reversal curse if you just train the model in the abstract concept level, meaning that every entity has like a unique token. You apply a unique token value to the entity and each relation. You will perfectly learn this reversal relation. But reversal curse does appear if you attach surface form names to those entities. And our analysis is that this is related to the long-standing binding problem in AI and in neural networks or biological networks. So which means that the transformer fails to learn consistent representations of the same entity if they switch roles as the perceived subject entity or the to be predicted object entity here. So there is more analysis in the paper, but we also designed a model based on JPA and memory layers that could solve the curse, but more in a synthetic setup. So how to generalize the model, adapt the findings to real world data and larger models is not clear yet. So there's still a lot of work to be done to understand deeper about the problem. So you might wonder, why do we care about implicit reasoning? Why do we care about the reversal skills? So the reason I care about them is because real tasks are inherently compositional, multi-step extrapolation, and also reversal thinking are common in complex reasoning. Moreover, because I'm thinking more about safety and security right now, I want to predict more failure modes, or at least try to say, given, like the knowledge about the existing or knowing failure modes of transformers or LMs, can we predict the new failure modes of them? So when do we expect them to fail, or in what can trigger the failure modes? All right, let me conclude the talk. I don't have many concrete to-do items listed here, but I have some cute pictures to show you. Some of you may know that I have been carrying my 2-year-old daughter at the conference, and so every week she surprises me with new words and new strategies, new ways to get to things that she couldn't reach before. So a capability of a young human being grows very fast. But on the other hand, we also teach safety at the same time. We teach her to look both ways when cross the street, wear helmets, do not attack others, be gentle with friends. So safety and capability grow alongside each other. Going forward, I really hope that we can balance the efforts spent on making models or agents more capable versus making them safer and secure. Yesterday, if you were in Nicholas' talk, he mentioned that if he were being generous, 80% of the papers maybe are about capability. If he's not generous, then less than that on like safety. But anyway, so I guess I want to mention that we really need to think about safety more and advance agent capability and safety together at the same time. And there is a lot more to do related to the theme of this workshop. Explainability and explanation can help a lot in this context. So with that, I will conclude here, and thank you very much for your attention. Welcome any questions and discussions.
Yeah, hey,
Hi.
The multi-hop thing that you guys were running on the just like general transformer, made me think about like universal transformer.
We did, yeah.
Implicit reasoning loop.
Yeah.
Would that solve a bit like the fact that like before grokking, some of the knowledge is kind of in previous layers, and like wouldn't you see like some kind of speed up in the learning?
Yeah. We actually have a related experiment in the paper. Perhaps we put it in the appendix, which is not very obvious because we were focusing on the vanilla transformer architecture. But there we used cross-layer parameter sharing. We do observe the OOD generalization is happening slowly. But we didn't wait until many more steps to see the perfect generalization there. But we do have a figure there to that will answer your question.
So, like, just more generally, what do you think, like going forward a bit, like yes, we're doing like chain of thought reasoning, and it's in token space, and we're doing this reasoning there. We're not sure if it's actually is reasoning or not.
Yeah.
Like, what do you think is the importance of like latent reasoning, let's say in the future for transformers?
I think it's very important. That's why I mentioned why implicit reasoning in one of the slides. Explain why it is very important. In particular, I think our group, in our group, we are particularly interested in understanding the parametric memory. How where the knowledge, the atomic knowledge is stored in the models, and how the model combine those atomic knowledge or facts to derive more and more complex queries. So I think it's very important. I personally is a big fan of that, rather than just collect more and more COT data and do instruction tuning.
Do you think we're gonna see like some massive models like that have this implicit reasoning like soon, or?
I think it's hard to analyze those very large giant models, but we are sort of a closing look at the recent Anthropic's approach, the attribution graphs. But that requires, I guess, a lot of compute and there is not so much progress on analyzing those bigger models, but I do think that's a very interesting direction to do. Yeah, thank you.
Thank you, Professor.
Yeah.
Now we'll be having first poster session and coffee break. And we'll meet again at